So welcome to the continuation of our work on motion. We were solving questions on motion. We have solved questions 1 to 3, and now we'll be starting with question number 4. Question number 4a says, figure 1.1 shows the distance-time graphs for 3 different objects, A, B, and C. And here is the figure 1.1. Let's see the questions on figure 1.1. It says, describe the motion of each of the objects A, B, and C by selecting the appropriate description from the list below. The first one is constant speed. Which of them has a constant speed? You know, this is a distance against, this is a graph of distance against time. So the slope of the graph gives us the speed. So which one has constant speed? The one with a straight line gives us the constant speed. The one with a straight slant line starting from the origin gives us the constant speed. And that is the line B. So the line B gives us the constant speed. So we write constant speed here. Constant speed. What about A? What does A give us? Look at A. A is a curved line and it curves in an anti-clockwise direction. Okay, so the curve A, it's curved in an anti-clockwise direction. What does that mean? That means the distance increases exponentially at equal time interval. For instance, if we decide to create equal time interval and we try to pick the distance within this equal time interval, for the first one, this will be the distance. The second one, this will be the distance. And for the third time interval, if you use straight lines, this is what you get. So you notice that the distance keeps increasing. The distance here is very large when compared to the distance here and here. That means the distance keeps increasing exponentially at equal time interval. Okay, so it shows that the speed is increasing. So we write increasing speed here. Increasing speed. So when the curve is, when it's curved in an anti-clockwise direction, then we know that speed keeps increasing. If it was curved in a clockwise direction, then it means the speed keeps reducing. Okay, that means the object is decelerating. Okay, but in this case, the object is accelerating. Now the third one, C. Look at the slope of C. What do you notice? C is a horizontal line. And when you have a horizontal line on a distance time graph, what does that mean? It simply means the object is stationary, it's not moving. So you write stationary for C. So C is stationary. That's all. Easy. And that's it. Look at the second question. Question B. Figure 1.2 shows the speed time graphs for 3 more objects, D, E, and F. So this is a graph of speed against time. Describe the motion of each of the objects D, E, and F by selecting the appropriate description from the list below. Look at D. You can see that the speed with respect to time, it increases exponentially in an anti-clockwise direction. What does that mean? That means the acceleration continues to increase, okay? Yes, the acceleration is not constant. Acceleration continues to increase. So increasing acceleration, that's what we have for D. Increasing acceleration. Increasing acceleration. So let us see E. E is just a straight line. That shows the acceleration is constant. That's E. And F, the horizontal line here, shows that the speed is constant. Okay? You know, the speed is not increasing with time. So F shows that the speed is constant. So let's pay for E and F. For E, the speed, E, the constant acceleration is constant. Constant acceleration, that's what we have for E. Constant acceleration. Why? Because we have a slope, a straight slope. That's why we call it constant acceleration. Okay? If the slope was curved this way, then we say the object is decelerating. If the slope is curved this way, then the object is, the acceleration is increasing. Yes, acceleration is increasing. If it is curved this way, the acceleration is decreasing rather. If the line is curved this way, there's deceleration. This is deceleration. This is acceleration. This is increasing acceleration. And this is decreasing acceleration. Okay? And if you have it this way, it means acceleration increases, then acceleration becomes constant, then acceleration begins to reduce. That means the object begins to decelerate. Okay? Good. That's it. So let me clean up all of this and write for E. Let me check out the graph for E again. So as for E, we have a straight horizontal line. That means the speed is constant, or you say acceleration is 0. Let us see what we have for F. Constant speed, yes, constant speed. Or you say the acceleration is 0. Constant speed. That's it. Let's go to the next question. Figure 1.3 shows a person bungee jumping from a bridge. The person is attached to a long elastic rope. So that's it. You have a long elastic rope. This is the person jumping. This is the jumper. So in 1.5 seconds, the speed of the jumper increases from 0 to 10.5 meters per second. Calculate the average acceleration during this time. What formula for acceleration? Acceleration is equal to v minus u divided by t. Okay. From this, what's the v? V is the final speed, which is 10.5 meters per second. So we have 10.5 minus u is the initial speed. What's the initial speed? You know, the speed increases from 0 to 10.5. That means your initial speed is 0. And then we divide by the time. What's the time taken? The time taken is 1.5. I stated here. This was places in 1.5 seconds. Second is the SI unit of time. So the time is 1.5 seconds. So let's see. 10.5 minus 0 gives us 10.5. And we divide it by 1.5. 10.5 divided by 1.5 gives us 7. Then put the SI unit of acceleration here, meters per second squared. Okay, so our answer is 7 meters per second squared. Let's take the next question. At one point during the fall, she reaches her maximum speed. State her acceleration at this point. Whenever you attain maximum speed, take note that acceleration is 0 meters per second squared. At maximum speed, acceleration is always 0. What can be said about the forces acting on her at this point? When acceleration is 0, what is force? Take note that force is equal to mass multiplied by acceleration. So whenever acceleration is 0, what does that mean? If you multiply mass by 0, you get 0. Okay, automatically the force is 0. So what that simply means is that there is no net force, or you say there is no resultant force. Okay, there is no net force, or you say there is no resultant force acting on the jumper. That's all. The next question. Figure 3.1 shows the speed time graph of a firework rocket as it rises and then falls to the ground. So the rocket rises upwards, okay? And let's assume this is the rocket. This is the rocket. Oh, yes, this is what the rocket looks like. Then you have flames. So the rocket rises upward, okay? So after some time, the flame stops burning. Let's assume at this point, the flame stops burning. That means all the combustible material has been exhausted. The moment the flame stops burning, that does not mean that the rocket stops moving. The rocket still moves upward a bit, okay, before it then starts falling downwards. And that is what this graph shows us, okay? So here, the rocket starts burning, it goes upward. At this point, the flame stops burning. All the combustible material has been exhausted. But that does not mean that the rocket will fall downwards. It will still move upward. but it will be moving upward slowly. That means the speed begins to reduce. The moment all the combustible material finishes, the speed begins to reduce as the rocket goes upward. So the speed reduces up until the rocket attains the maximum height. Okay, at the maximum height, the speed of the rocket is equal to 0, and that is what you have here. The speed here is 0. Sorry, here, yes. The speed here is 0. This is what happens at maximum height, okay? So this is what happened. The rockets launch from rest, then it begins to accelerate upward, accelerate, till all the combustible material got exhausted, okay? Here, all the combustible material got exhausted. And then the rocket kept moving upward, but the speed was reducing. So that's why the speed time graph shows that the speed is reducing until the speed gets to 0 at maximum height, okay? Okay, the speed gets to 0 here at maximum height, and then it starts falling downwards, okay? So it starts falling downwards. That's why the speed is negative, because it's falling in the opposite direction to the direction in which it rises. So its speed it starts falling downwards till it lands. When it lands, its speed suddenly becomes 0. That's why the graph looks the way it is, okay? Good. So this point A does not mean that the rocket starts falling, no. This point A is the point where all the combustible material has been exhausted, okay? But it does not mean that the rocket starts falling. It keeps moving upward, but at reduced speed. Now let us answer the question on this. The rocket runs out of fuel at A. It reaches its maximum height at B, and it returns to the ground. State the gradient of the graph at B. You know, at B, that is when it reaches its maximum height. Yes. So at maximum height, what will be the acceleration? Let me see. All right. So the rocket moves upward, it accelerates upwards, then it begins to decelerate. The speed starts reducing till the speed gets till the speed becomes 0. That's at maximum height. But take note that at maximum height, it is still under the influence of gravitational field strength of the Earth, okay? That's why we say the gradient is 10 meters per second square, okay, which is the acceleration due to gravity on the Earth. So gravity keeps acting on it. So whether you put plus 10 or minus 10, it does not matter. Gravitational field strength is 10 meters per second square, and it acts towards the center of the Earth. State why the gradient has this value. Why does the gradient have the value of 10 meters per second square? Because it is under only the influence of gravity, and drag is equal to 0. That means there's no air resistance. Take note that when an object is not moving, when an object is at rest, drag has no influence on it. The influence of air resistance is 0. Air resistance will only act on objects that are moving in the air, okay? That's why the value of the slope is 10 meters per second square. The slope at B, when it's not moving, okay, at maximum height, the slope has the value of 10 meters per second square, acceleration due to gravity, okay? Because drag does not affect the slope. Okay, let's go. State and explain the relationship between the shaded areas above and below the time axis. So look at the time axis. Remember, I said that from point 0 up to A, the fuel is burning. Then at A, the fuel has exhausted. But that does not mean that the object starts falling downwards. No, it keeps moving upwards, but the speed begins to reduce. That's why this slope goes downwards. It shows that the speed is reducing. At maximum height, speed is 0. Okay, that's what we have here. 0 is here. Okay. Then from this point, the object starts falling downwards. So the shaded portion above, it shows the plot, it shows the graph when the object is moving upwards. While the one below shows what happens to the motion when the object is moving downwards. This is the motion graph when the object is moving downwards, okay? And the one above the time axis is the motion graph when the rocket is moving upward. So that is what we're going to fill on that space down here. State and explain the relationship between the shaded areas above and below the time axis. The shaded area above the time axis depicts the upward movement of the rockets, okay? And at that time, the rocket is moving against the gravitational field of the Earth. Against the gravitational field of the Earth, okay? Or we say against the force of gravity. Good. Then the shaded area below the time axis, depicts the downward movement. Depicts the downward movement of the rocket. Depicts the downward movement, the movement, E-N-T. Sorry, let me just fix that. Depicts the downward movement of the rocket. Under the influence of gravity. That's it. Another rocket of the same size and mass opens a parachute at point B on figure 3.1. Sketch a possible graph for its speed from B until it reaches the ground. So another rocket opens a parachute at point B. Where is point B? That's the point where we have the rocket at maximum height. So another rocket, after traveling, the fuel gets exhausted at A, and then it starts moving slowly till it reaches maximum height. At maximum height, it then opens a parachute. Once that rocket opens a parachute, what happens? The parachute makes the rocket to travel slowly downwards, okay? The parachute makes the rocket travel slowly downwards. That's the effect of the parachute on the rocket. So the rocket starts traveling downwards slowly. Okay, that means, let me erase this so I can draw the graph, because we are meant to plot. So from B, then we draw the curve. And we indicate that it is traveling slowly, and it attains a uniform velocity. So it attains is less final velocity compared with the original slope, whereby the parachute is not connected. You know, initially without the parachute, it attains a final velocity of this value, though on the negative axis because it is moving downwards in the opposite direction from the direction in which it was launched. You know, it was launched upward. That's why the upward movement is plotted upwards, and the downward movement is plotted below the time axis. But it attains a final velocity. It attains a final downward velocity that is lower than the initial final velocity, and that's why the slope attains a uniform final velocity at this point here. Okay, and this final velocity is called the terminal velocity. Yes, so that is what the graph looks like. So let me claim every other thing that does not constitute the answer. Okay, so that the answer can be clear. Yes, so that curve I've put there, that is all you need to put. All of these are not necessary. And that's it. Once you get all of this done, then you get the full marks for that question. Let's go to the next one. So this is another question. A free-fall parachutist jumps from a helium balloon but does not open his parachute for some time. Figure 1.1 shows the speed time graph for his fall. Point B indicates when he opens his parachute. So that's it. A fall parachutist, that means when the parachutist jumps from a helium balloon, then it starts falling towards the surface of the earth. You know, when he jumps, initially he has a speed of 0. So as he's falling towards the earth, then he starts accelerating, okay? He starts accelerating uniformly. But after some time, drag begins to increase and drag begins to reduce the speed, okay? That's why initially it has a uniform acceleration of 10 meters per second squared. Then the acceleration begins to reduce. Why? Because of drag. Drag reduces the acceleration till the object attains a final uniform velocity. Okay, then you open the parachute. Once you open the parachute, the velocity will drop to a low steady value. Yes, that is what happens to parachutists. That's why parachutists survive. Okay, parachutists survive when they land because they land with a low steady velocity. Okay, unlike when they do not open the parachute, when they would land with a very high velocity. For instance, they might be landing at a high velocity of probably 200 meters per second, okay, without the parachute. When they use the parachute, they'll be landing with a final velocity of probably 3 meters or even lower than 3. They could land with a velocity as low as 1 meters per second. Yes, or even 0.5 meters per second. That's why they survive it with the parachute. So that is what this graph shows us. It shows us how the parachute saved the life of the parachutist. So now let's go ahead and answer the question on this. Let me erase all these unnecessary lines so that we can focus on the parts that constitutes the answer to the question. Let's go. The question says, state the value of the gradient of the graph immediately after time t equals to 0. Immediately after time t equals to 0, what will be the value of acceleration? Yes, the slope is acceleration. Immediately after jumping off, the acceleration is 10 meters per second squared. Why? Because immediately after jumping off, drag is 0. Okay, that's why the gradient will be 10 meters per second squared. Good. Explain why the gradient has this value. Because it represents the gravitational field strength and also drag is equal to 0 because the speed is very low. State how figure 1.1 shows that the acceleration decreases between time t equals to 0 and the time to A. between time t is equal to 0 and the time to A. So between time t is equal to 0, between the time here and the time here. So the fact that the graph is curved in the clockwise direction, it shows that the acceleration decreases. Yes. Look at the acceleration here. The slope here is very slant. But look at the slope here. Okay, it has almost become a horizontal line. That shows you that the acceleration has reduced from t equals to 0 to the time at A. Okay, good. And at this point, the acceleration has become 0 completely. That's what this flat line means. Okay, good. So the fact that the curve is in a clockwise direction, it shows that acceleration continually reduces from 0 up to A. Okay, then after A, the object travels at a constant speed. And that's what we have, that's what this horizontal line depicts. So let's go and fill our answer there. The curvature of the slope, or you say the exponential decay. So that's curvature to the right shows exponential decay. Not exponential decay, but it rises exponentially and then maintains a uniform value. So the exponential rise of the curve before attaining a constant value shows that acceleration decreases. That's it. Explain in terms of forces what is happening in the section AB of the graph. You know, section AB, that is when the slope is completely horizontal. Okay, so when you have a slope that is horizontal like this, what does it mean? It means the speed is constant. And when speed is constant, what is the value of acceleration? 0 meters per second square. Okay, good. This shows that there is no acceleration. Okay, yeah. And whenever acceleration is 0, what's the value of force? You know that force is equal to mass times acceleration. So when your acceleration is equal to 0, multiply the mass by 0. What will you get? You get 0. Yes, so whenever force is 0, it means there is no... Whenever acceleration is 0, it means there is no net force acting on an object. So let us go and fill the answer here. So explain in terms of forces what is happening in section AB. So at AB, there is no net force on the object. There is no net force on the there's no net force on the what? Is it object? Parachutist, yes, then on parachutist, on the parachutist. Okay. This means the force of drag, okay, or you say the force of air resistance balances the force of gravity. That is the force of gravity on the parachutist. Good. So as the force of gravity tends to bring the parachutist downwards, the force of drag tends to oppose the motion, that is, opposes the motion of the parachutist. So both of them are equal, so they balance each other. When they balance each other, that means the net force equals to 0. That's why there's no acceleration, okay? When the net force on an object is 0, that means the acceleration of that object is 0. And whenever acceleration is 0, it means there's no net force acting on the object. Let's go to question D. A second parachutist of the same size and mass jumps from the balloon with a larger parachute. He then opens his parachute at point B on figure 1.1. Sketch a possible speed time graph for his fall after he opens his parachute. Okay, so when you are using a bigger parachute, what does that mean? That means you attain a smaller final speed, okay, than the first parachutist. Yes, if you are using a bigger parachute, then this is what happens. At B, when you open your parachute, then your speed drops to a lower final speed. Yes, so this is what your graph looks like. Yeah. So you attain a lower final velocity. And that's why then those who jump from a moving plane, if you have watched Mission Impossible, yes, when Ethan Hunt jumped from the plane, he used a big parachute. And that is why he was able to land successfully. Though you are advised not to try that at all. Let's go. Question number 7. Underline the vectors in the following list of quantities. Number 1, density. Is density a vector quantity? No. Number 2, we have energy. Is energy a vector quantity? No. Force. Force is a vector quantity. You underline force. Mass. Mass is not a vector quantity. Velocity. Velocity is a vector quantity. Volume. Volume is not a vector. Volume is not a vector quantity. So you leave volume. Question B. A small metal ball is projected into the air with a velocity of 40 meters per second, vertically upwards. The graph in figure 2.1 shows how the velocity changes with time until the ball reaches its maximum height. So this graph here shows the plot of velocity against time. Use the graph to find the time at which the ball reaches its maximum height. So look at this graph. You know, at maximum height, what happens to speed? Speed is 0. Okay. So you just trace at 0. Where does this slope hit point 0? That's what we have here. That is 4.1. Okay. So what's the time at that point? You write 4.1 seconds. That's all. What else do we have? What's the deceleration of the ball? How do you get the deceleration of the ball? Deceleration is what? Deceleration is acceleration is final velocity minus initial velocity divided by time. Well, deceleration is initial velocity minus final velocity divided by time. So let us pick our initial velocity, we pick our final velocity and the time. So the objects from the slope, the object started from 40 meters per second. This is our initial velocity. So we have 40 minus the final velocity is the velocity when the object lands. Okay, and we have that as the velocity here, which is 0 meters per second. Okay, so we have 40 minus 0 divided by what's the time taken? The time taken is 4.1 seconds. We divide that by 4.1. Okay, now 40 minus 0, that gives you 40. Now let's divide 40 by 4.1. Let's go. 40 divided by 4.1. What does that give us? It gives us 9.76. So our deceleration is 9.76 meters per second square, which is very realistic. You know, our deceleration should be close to the gravitational field strength. Yeah. So you get 9.76 meters per second square. Maximum height. How do you get the maximum height? The maximum height is the area of this right-angled triangle. So how do you get the area of this right-angled triangle? What's the formula for calculating area of a right-angled triangle? So our maximum height is the distance traveled, and which is the area of the right-angled triangle, okay? And the formula is half base times height. What's the base? The base is from here to here, that's 4.1. What's the height? The height is from this lower level to this higher level, which is 40. Okay, so we have half times 4.1 times 40. Good. And that will be the same thing as multiplying 4.1 by 20. And that will give you 82. Good. So we get 82 meters. And that's the distance covered. So maximum height is half times base 4.1 times height. Height is 40, and that will give us 82 meters. And the last question says, add a line to the graph to show how the velocity of the ball changes after it reaches its maximum height. Your line should extend to 6 seconds. So after the object reaches its maximum height, what happens? Then the speed starts increasing as the object goes downwards. And that is what this line here depicts. So let me erase every other unnecessary line so I can focus on only the answer to the question. So that's it. So that's it. Let me remove this from here because I've already solved it. Take note that this is supposed to be a perfectly straight line. So you make sure your line is as straight as possible. And that's it. So this shows how the object accelerates downwards, okay? So if it's accelerating downwards, the speed starts increasing with respect to time. And that's what this blue line on the right-hand side depicts. That brings us to the end of our discussion on this past question. So some other past questions will be solved. Stay tuned. Thank you for listening. Do have a nice day. See you when the next video is released. Goodbye.